Hello folks, and welcome back after a 3-year break. Nearly to the day was the last time I made a video about this topic. And its topic is our Tesla Model 3 battery management system controller. So for those of you who might be new to the topic, I will put a link in the description to some of the videos that I did 3 years ago, where we did an awful lot of reverse engineering work on the BMS communication. And the short version is that it is a derivative of the LT ISO SPI mechanism. And what Tesla did was they basically stretched the pulses in the ISO SPI train to make their own version of it. So it will not work with off-the-shelf commercially available LT communication chips and boards. So hence the need for the rather kind of a roundabout way that we're going here. So when that we had last looked at this, I had been working on an FPGA design that I had hoped would be able to give us a kind of a more off-the-shelf, as it were, method of communicating. I haven't done any more work on that since then. There's been an awful lot of things going on with me over the time involved. But I had put everything that I'd learned up on Github and the Open Inverter forum. And if I'm quite honest, I had assumed that by now somebody would have taken, some or all of that information and gone ahead and made some kind of a mechanism for talking with the Model 3 BMS. And because it's probably the topic that over the years and even still in recent weeks I still get contacted about when I'm going to have something available for this. So I had assumed, as I say, that there would be something brought out by a third party by now, but sadly not. So about 6 months ago, I had done a design with the STM32 and had a few of those prototypes made, and that's what we're going to be working with here today, and we're going to show you. Since then, I have been trying to translate my hardware design tools from Design Spark to KiCad, and I redesigned this board in KiCad and just cleaned up a few things and deleted the old ESP Wi-Fi module and a few things like that. So we'll have a look at that design here as well today, and hopefully in the next few weeks we'll be in a position to start putting some of these boards in the web shop. Now in the meantime, obviously testing and development here is very much ongoing, as is still me picking up where I left off with everything that's gone on in between. It's not exactly straightforward to pick up. So first thing that you might recognize here is what I call the Mini Musk. Now the Mini Musk's job is to basically pretend to be a big Model 3 battery module, and there's 4 of these in a pack. There's what's called, I guess, the long and the shorts. The shorts have 23 cells each, and the longs have 25, giving us a total of a 96 S pack. Now this fake version here simply has 25 18650 cells wired in series and rather dangerously wired up with some wire wrap wires here to our I guess these are called BMBs apparently within the whole Tesla thing, battery management boards, and each one has got 2 of these Batman chips on it. Each of these can manage up to 16 cells each. So in this case there's 25 cells here, but when we get deeper into it here, we will note that we're only reading 23 of those cells. And the reason is this board here that I'm using, Sod's Law, is one from a short module. Now you can access the all 16 cell voltage registers on these things, and I'm sure there probably is a way to configure them to read all 16 if you wished. It may even be that the hardware on here simply doesn't have them wired up, but I haven't delved too much into that part yet. So let's have a quick look here on the bench at our little test setup. So obviously what we've got is our fake Model 3 pack. Now I've only got one, obviously there'll be 4 of these in a full pack. We've got our ISO SPI wiring here, which is our 2 wires, and that is coming over here. If I move the camera a little bit, you're gonna, there it is. So you're gonna come down here and you're gonna find this little mess job here on the bench, and this is my prototype board. I think I had 10 of these made up. I haven't bothered fitting the pin header to this, but I'll show you that later on. And basically all we've got going on here is we've our ISO SPI comes in here. We've got 12 volt power coming in here. STM32 F103 C8T6. Batman chip there in the middle, bit of supporting circuitry, power supply, Wi-Fi module, all that kind of thing. And I've got my little Saley logic analyzer here connected, because I've obviously broken out the standard SPI signals here onto a header so that we can do some reverse engineering work on that. Because we're still very much working in the dark on this. Tom Debris did a load of work on this back 3 years ago, worked out where the cell voltages were and things like that. So I've done a little bit more now over the last couple of days, but it basically, yeah, it took all day to work out a few simple signals, but yeah. So this will be the little controller board. As I said, I'll show you this in the enclosure and so forth soon now. But let's dive straight in here and we'll show you on the screen what I've got for you. So it's the standard open inverter web interface. Let me hold the camera there so you can see my beautiful face. It's the standard open inverter web interface here. Now at the minute the setup stuff here doesn't really do anything, but we'll have some basic configuration working here soon. This is all very basic stuff, so I'm not really focusing on this at the minute. I'm more focusing on being able to talk to the Batman chips. So you'll be able to select Model 3 or Model S BMS, because the hardware on this, there's also hardware on that to support the Model S X slave BMS boards. You'll be able to select things like balancing on and off and what your balance voltage you want and all that kind of nonsense. You'll also be able to connect a current sensor here. Again, none of this is actually coded at the minute, just want to stress that. So just some basic menuing. So for measuring current, you'll be able to use an analog sensor, so be that a shunt or what's the Hall effect or the ISA shunt. I think there's some ISA shunts out there that just do current, so this would be probably the ideal thing to use them with. So under spot values at the minute, I've been kind of building this up, and so the basic stuff like op mode and state of charge and charge limit, discharge limits and all that, that's all yet to be kind of worked out, but we've got some values here populated, as you can see. So we're getting our total voltage of our connected pack. Now at the moment that is just our 25, or in this case 23. I should note something as well, it's quite interesting. This value here that you see is actually the exact voltage of the 25 cells. And you might think, hang on a second, didn't you just say we're only monitoring 23 of them because this is from a short pack? Well, that's true. However, I'm just going to cheat here a little bit. You look at that UDC there, okay? Now we're going to shoot down here to the bottom, and we're going to see two parameters called chip V1 and chip V2. So these values here, as I said, there's two Batman chips on each of these boards, and each of these Batman chips, as well as reporting the cell voltages, also report I call it the chip voltage. So it's the voltage of, like, say, between the most negative cell and the most positive cell that's connected. Now I've got I got a dead cell on this, as you'll see. So you'll see there's a little bit of a difference, or not a dead cell, I've just got a bad cell in there. I bought these things for €1 each, so I don't really care. But you'll see there's a little difference in them, but when you add those, then basically what you get is 102 volts here, which is our UDC, because that's all that we're doing here at the minute, is we're just adding the two chip voltages. So if I get my multimeter on the old DC volts, don't know, you probably won't be able to see this, of course, knowing my dodgy camera work. So if I get my multimeter here and stick this on most negative, most positive, come on, 101.8, 101.9. I'm seeing 101.9. That's what I'm seeing on that meter. And yeah, we're seeing 102 here on our stack voltage. But when we go down here and we start looking at the cell voltages themselves, and I'll just refresh this a couple times just so you see they're actually live. I'm not, you know, faking this. They're not static. You'll see them kind of changing around there. Now, you'll see here that we have 8 cell voltages perfect here. You'll see that I've got one at 0 volts here, cell number 9, and one at 184 millivolts. Now, I'd actually thought that I had a bad cell or something in there, or a bad connection, but what I'd been doing yesterday when I was trying to find signals, and I'll kind of show you a little bit of how I was doing that, not very smart of me. See, this is like a mini Elon brain, right? Now, you guys ever seen the Terminal Man? Okay, so you know where they're putting the probes into the guy? Okay, so this was me here yesterday. Now this is a 64-pin QFP package, and it's got all the cell, you know, it's got the cell voltage measurements and so on there. So I'm in there probing with the damn thing, right? Because I'm trying to find what signals are where, and you know what cell register matches up to whatever voltage. And of course I'm slipping and the probes are going across the thing, and things. There's little sparks coming out of it and that. So basically I'm not very good at Elon brain surgery. So I think I've brain damaged one of the Batman chips. Okay, so I've basically damaged Batman. Okay, I'm sorry. However, like I say, these two here should be reading normally, but as I said, I think I've damaged Batman. I thought it was, I don't know. What leads me to believe that it's a damage to those cell channels is that, number one, I was seeing sparks coming off the chip, but the actual chip voltage measurements are fine, right? They all add up. So I think I have just killed these two channels here, and if we look at the actual raw data coming over SPI, we can see that it's missing those two channels. So I'd be very interested when we get a few of these out to beta test, just to make sure that this isn't, you know, something silly I've done in the software, but I don't think it is, but you know. Anyway, so basically what we would normally have here is we'd have our 12 we'd have 12, sorry, not 12, 13 cells, because we start at 0. So the first Batman chip, this one nearest us here, is the first, in this case, 13 cells. And then the second Batman chip, one up here, for the short modules, would do the remaining 10 cells. And if we look here, that's should be pretty much what we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So second Batman chip is working away. You'll see that we have a gap here, 13 and 14. That's fine. That's just me messing with the array alignments, because, you know, obviously the only thing I'm probably worse at than Muskian brain surgery, excuse me, is C programming. So anyway, obviously, if this was a full pack, we'd be going all the way down here, and we'd have all the way up to our 96 cells. So hopefully, well, as I say, when I get a few of these out to folks, and they'll be able to connect them up to full packs, we should be able to see all of these cell voltages populate. So I will be looking for some beta testers, maybe 2 or 3 people that would be willing to assist. Next thing that we have here are the die temperatures. So these are considerably higher than the current ambient temp. Ambient temp in this room now is about 14-15 C. So these are a lot higher than that, and it was it was great fun finding those. Now, because I know there was a guy on the Open Inverter forum that had actually found these back when we were doing the initial work, and I was looking at them here yesterday. I thought, no, that's, I didn't like it. I spent a whole few hours going round in rings with this thing, because I didn't quite believe that, because they were too high. And it wasn't until I came in here with a can of freezer spray and actually started with the thing of the freezer spray just freezing little points on the board, and when I froze the actual chips, those temperatures flew down, but then came back up quite quick, because there's a lot of work going on, because we're currently, you know, polling here continuously. So there's a lot of work going on those chips, and if you put your finger on them, they do feel, they do definitely feel that kind of temperature a few degrees above. So there'll be 8 chips in a complete stack, and we'll be able to populate obviously all of those temperatures here. So coming back down here to what some of my probing got me, this value here, each board has a 5 volt regulator on it. It derives its 5-volt supply for the Batmans from the full pack, or the full brick, I guess you might call it, voltage that's on there. So there's a reading for that here. I just refreshed. Yeah, there it goes. It's changing around a little bit. It kind of jumps around a small bit here. Likewise, the stack voltages were actually a little bit easier to find. So right, that is a little look at the web interface. Now obviously it's very much under development at the minute, but as I say, the kind of critical part of this now is to kind of work out, you know, so we can read the voltages, we can read the temperatures, we can read the 5-volt regs, we can read the chip, full chip voltages, and so on. So alright, I'm going to get a board here and a little enclosure and stuff, so I'll be able to show you how that looks. We'll also show you the procedure for transplanting the Batman chip on there. We'll come back then and I will show you a little bit of the work with the Saley logic analyzer, just how to, because there's a few tricks in there that I've since learned the hard way. So alright, back in a jiff. Recording. Alrighty folks. So, tell you how crazy my life gets sometimes, okay? This morning, I was loading a half a ton of concrete blocks into a trailer. Now I'm doing microelectronics. I'm making videos. Alright, so, what we've got for you today is, I don't know what this will end up being, an instruction or an intro or whatever, but it's for our hopefully new and semi-exciting Model 3 and also Model S BMS controller board. So this section here, let's say, will be relevant to you if you want to use this with the Model 3 battery modules outside of the original pack. So I can't believe it's been like 3 years. So Model 3 years since I did the initial work on reverse engineering the Tesla specific ISO SPI stuff and all that. So I'll put link in the description to some of those videos for those of you that might want a bit of background. But however, so what we have here is an STM32 F103 based master module for our Model 3 and also hopefully the Model S and Model X modules as well. So at the time of making this video, I'm still just building up the software and the web interface and all that kind of thing here. So what I focus on today is how we actually use this to communicate with the Model 3 slaves, or in Tesla parlance, BMBs, battery management boards, of which this is actually one of them. Now, I'm not going to go back over all of the findings and history and all that of working out this stuff, but as I said, I'll put a link in the description for those of you that want some more detail. Suffice it to say that the flavor of ISO SPI that comes in and out through these pins here on the BMB boards is unique to these chips and our Musk. So again, at the time of making this video, you cannot use off-the-shelf ISO SPI chips to communicate with these guys. So how we do this then is by a little bit of brute force, I suppose. We're going to remove one of these chips here, so either will do, and place it on our board. And then we can communicate with that chip using standard SPI from our STM32F1, and then that'll get translated into the correct ISO SPI pulses by this chip, goes through our little transformer and some filtering circuits, and then gets spat out. And hopefully, if all of this goes to plan, you'll be able to read the cell voltages, 2 temperature sensors, and also trigger balancing should you wish to do that on your Tesla battery management boards. Now, this product has been a while coming along for various reasons, but there's always been something in my way. So I'm hoping now I can kind of dedicate a little bit of time to getting this guy at least into a kind of an alpha release state. So the board that you may get in your kit may be a little bit laid out differently to this one, depending if I find any design errors or build errors on this. So, but no matter what happens, you'll basically get a board like this. You'll get a Wi-Fi module that you'll need to solder onto it. That'll be pre-programmed. The STM32 will be pre-programmed, and you will find a big glaring gap then on your board in the shape of where the Batman chip should be, because I will not be supplying Batman chips to you. You're going to have to hunt those down for yourselves. Now, the most common, probably easiest to get version will be at the actual BMB boards themselves, because over the years people have had a tendency to remove these and put third-party BMS systems in there, and in my mind, the less said about that, the better. So what we're going to focus on doing today is going to be removing one of these Batman chips. I should also point out that this chip here is the very same chip that's on the high voltage controller, so you can actually harvest that chip. You can harvest this chip basically from the high voltage controller or one of these BMB boards. And as a bonus, if you get one of these BMB boards, you get 2 Batmans. So what I'm going to do is I'm going to just get in here with a little magnifier firstly and just check, because it has genuinely been years since I've looked at these. Check where my orientation dot is on here. Oh, there's a little cape coming out of the Model 3. For those of you that might be interested, I'll read out what it says on there. This particular one says 1912 T2 minus A6 PZ4 6667, and there's a 3 on its side as well, of course. There's the dot. So the pin 1 dot is here on this corner when I have these connection points facing away from me. And let me see here on my board here, the pin 1 dot is then there. So basically what we'll want is we'll want to have this board oriented with the Wi-Fi module facing away from you. So we'll try and basically orient these so that when you're transferring the chip over, you have less kind of likelihood to have a problem. So let me just triple check that. Yeah, there's my pin 1 dot there. Hello, Elon. Hello, Greyman. Hope you like what I've done with Twitter. Oh yes, I love it, Elon. Well done. Thank you. Right, pin 1 dot. So now, as with all Muskian things, Elon has secreted his goo on here. Haven't really found a super effective way of defeating the goo other than just put a bit of this stuff in there and heat it quite heavily. Keep it family friendly, as they like to say. So, alright, going to be using my thrusty hot air station here. This is a serious little beastie. I think it's 3.5 kilowatts or something. And it's at 440 degrees for those of you that might want to play along at home. Can't imagine it would be a good idea though. So I always wait for this to come up to temperature. You can tell by the lights pulsing in here. And then just start heating. Just very gentle with the scalpel, making sure we've lots of heat in there. We don't want to strain any of the pins. Come on, Elon. Up you come, buddy. There he is. And I'm just going to drop him down. I'm actually going to drop him upside down on the mat. And the reason for that is that what we don't want to do is to plop him back down on here. Finished with that for now. Plop him back down on there while there's a big lump of flux or any kind of goo sitting on the back here. So what I tend to want to do with these, this cheap mat is bulging. Don't buy a cheap mat. Just check the pins while I'm in here as well. Yeah, looks like it came off quite cleanly. Thank you, Gabriel. No problem, Elon. Okay. So let's flip them over. Make sure we kept our orientation. Oh, there you go. Look at you with your cape on you. Ooh. Look at that. There's our pin 1 dot there. So, Elon. Again, I'm just being total paranoid job, making sure that got the orientation dot where I want it. Want to annoy Mr. Musk. So what I'm going to do now is I'll put a small little bit of flux on this. I don't want to go nuts because you need to be able to line up the pins. What I'll do now again is just slide the knife in underneath Elon and just plop them down there. And just use the blade to roughly position his Muskian form in the appropriate place. There we go. Look at you. You're killing it, Elon, I believe is the right phrase these days, isn't it? Oh no. No. It's not quite killing it. He does have a little bit of a problem child down there at the end. But anyway, I won't bore you with all this, so I'll come back when we're all gone. When we're not on. Okay, so got Batman soldered on. I've given him a reasonably good visual inspection. Don't think of any shorts or opens or anything stupid, but hard to know. But we'll power it up here and see what kind of a pop it decides to make. Well, to my surprise, it didn't go pop. There's some nice flashing lights on there, and we're drawing about 70 milliamps, so don't think we've any problems here with this. So I'm going to give this a clean up, and I'll show you then the enclosure that we have planned for this guy. Alright, so got our Batman chip on there now, and I've also put a little header on here. This is just optional, it just breaks out the normal SPI. And this one here, I'll probably populate that as well just for my own testing. That's the ISO SPI header there. I don't know what's wrong with the camera, it's looks like it's furring around the edges, but anyway, this is our little header. It's 48 pin, just AliExpress. header, just clips on like that. And once I know that these boards work, I'll solder this on, and then it has a nice little enclosure that it goes into like that. I think I do have to, I think one of the reasons was I think I have to round the corners. You can't really see it too well there. Yeah, I think I have to round the corners of the board. You'll see the way it's kind of just a little bit over it there, so I probably will have to do another batch of boards before I ultimately sell these. But anyway, you've got a metal plate then in your head, obviously just like me, that goes on the bottom, and that's your, hopefully this will be our Model 3, a Model S BMS controller thingy with STM32. Recording. Alright, so just very quickly show you, this is our actual board. This is just the same as what we've got here. Broadly this will be what I have available. As I say, the one I've done in KiCad now is a little bit different. I've just moved some components around, got rid of this old legacy Wi-Fi module and a few things like that, but pin out and all and the functionality will be the exact same. I'm debating whether I will bring out the second ISO SPI interface from the Batman chip and put another transformer. I'll probably use the same transformer. Yeah, I think it has multiple ones in it. I'll have to check that out. Because they have two interfaces to allow for broken communications in one channel. So this is our board broadly, as I say. The one I'll end up selling hopefully in a few weeks. Just of different component placements, but everything else functionally will be the exact same. There will be an enclosure. I'll put a link for that enclosure in the description and other wiki pages and stuff like that. But it's a commonly available kind of automotive header. These are just, I just get them from AliExpress. I don't get enclosures and stuff now from more traditional suppliers, because these are the first things to go once there's any kind of a component shortage. And it's got a plastic enclosure like that, so you've got your board goes in. As I said, I've got to put the alignment holes and stuff in this, but this is all just prototyping at the minute. And there's a nice little metal cover that goes on the back, and that'll ultimately be our our Model 3 BMS controller. So let's go have a quick look here at the KiCad side of things. Okay, so this is our KiCad PCB design here. As I said, I'm kind of learning this now, so I decided I'd do this board in KiCad because it's a new design kind of thing, so I don't need to worry too much about legacy circuit diagrams and things like that. So we'll have pretty much, this is our Batman chip here. We'll have our SPI breakout, as you see, just for development work, our Ethernet transformer, and some clamping circuitry and so on. So we can do the fancy 3D view, which we do quite like in KiCad. So you'll see there it is a little bit laid out differently to, let's bring that over there so you can see it. It is laid out a little bit differently to the one that I just showed you, but functionally it's the exact same. You'll have the same pinouts, connections, all that sort of thing on there. And as with all of my work and designs, this guy here will be it'll be PDFs, schematics, board layout file. Gerbers will be free on GitHub, and if you want the design files, they'll be available through Patreon for a certain period of time. Then they'll be free. But we'll be doing that only when, you know, we know that everything's working 100%, which is why I didn't go ahead and do any releases on the current one, because that's just in the prototyping stage still. So that's our hardware basically, and I'll be showing you how we harvest the Batman chip. Now the Batman chip is not, you cannot buy this guy, okay? You can't go on DigiKey, Mouse or Radionics anywhere and buy this particular chip. You're going to have to harvest it either from a BMB board, on which there's 2 on each one, or you're going to have to harvest it from the high voltage controller from a Model 3 battery pack, of which there is 1. Alright, so let's have a little look at the raw data, shall we? What we're looking at here is a plot from, I can kick that off there. What we have here is a plot from Saley Logic. Now the Saley that I have, the little one, they don't sell that anymore. I got that years ago. It was free actually from Adafruit. The ones they have nowadays are super cool, but of course, you know, I can't exactly afford them. So I'm using this little guy here, but I have to say it's impressive that even their latest PC software here, number one, they have a Linux version of it, and number two, it works with this ancient version here. So what we're looking at here is a typical request response over SPI, and you're looking at the logic level SPI here that's coming from, well, to and from the STM32 into and out of Batman, and Batman then translates that into the Elon version of the ISO SPI pulses, shoots that down the line into the fake Musk pack, and the fake Musk pack then answers Batman on our controller board, translates that back into standard logic level SPI that we have here. For the nerds out there, it is, remember this now, I should, it's SPI mode 3, of course, because Elon, 1 megahertz clock, and clock return to 1 when idle. So all this info, there's like tons of info on this. It's all in the past videos and on the GitHub, and I believe the old thread is probably still there on the forum as well. So alright, so each time that we want to access a register, I won't go too deep into this, but each time that we want to access a register in one of the Batman chips on the BMB board, we've got to send a request. So that's what we're doing here. So you're going to see 4A00 C900. This is a request to access one of the registers, and I'll tell you which register now. Let me just stop that for a second. We'll pull up our software, and I have all these. 4A is basically register D, and register D here is one of the cell voltage measurements, so that's kind of handy. So let's go back to Saley, back to live, and okay, so register D is one of our cell voltage measurements. Oh, in fact, I know what this is. You know that one on the web interface where we have the missing value and the very low value under it? That's what we've got here. So where we see the response FFFF, that's actually the missing cell voltage measurement. And this one here, do we see a low value like, oh yeah, did I have some fun with this? So I'm going to read this as like 08FA or whatever here, because guess what? Some of, but not all of, the responses in the registers are byte swapped. Not bit swapped, but byte swapped. So these are all 16-bit transactions, okay? So all transactions with Batman are 16-bit. And basically, some of them have their bytes flipped, so that's great. Oh, I'm too old for this. Anywho, so if we look at this one here, this one's probably going to make a little bit more sense. Let's have a little play here with this guy. So let me pause him and we'll show you how this works. So let's pause him, okay? And we're going to read this as C4-1E. So I'm going to get my trusty phone out. And I've got this, got a binary hex converter thing here. So I'm going to put in hexadecimal C4-1E. And that comes out as 50206 decimal. 50206. So we're going to get ourselves a calculator. We're going to go 50206 and we're going to divide that by 12.5. And that is going to give us that number. So 4016.48. And that is, folks, the cell voltage for that particular cell. And basically then the rest of the cell voltage registers work that way. They use the same divisor or multiplier or whatever you want to call it for the 5-volt regulator. They did not use, however, the same, and that was great fun, for the stack voltage. So I kind of had to, it was making crazy here. I had 2 power supplies going on trying to fool this thing and trying to get a voltage and a reading and another voltage and another reading. So it's no wonder I gave Elon a bit of a bad hair day there. But anywho, that's what one transaction. So basically, if we look here, let me pull this down so you can see the full transaction here. So this is the enable line or the select line, call it what you will. So basically you're going to see is this is the response back, this is our request, and this is the response back, and you'll see we've got like a lot of empty data space here. Don't know if you're even able to see the stupid mouse pointer, probably not, but anyway, there's a lot of empty data space there after this, and the reason for that is, again, we've only got one of a possible 4 BMB boards on there. So if we had a full pack, this would be fully, you know, this would be fully populated. The response from each register would be fully populated. So as I said, I'm not going to get too deep into this. If you want more of this crap, let me know. Otherwise, you can go back to the 3-year-old videos and drive yourselves crazy. So okay, that is our basic data. We've shown you the web interface, we've shown you the board. Just a very quick look at the software here. This is super crude at the minute. Tom Debris did a lot of work on this, basically ripped off what he did, translated it into STM32, and I've been, as I say, hacking away, working out combinations of what Tom figured out, my own bits and pieces here, and this is kind of dangerous because it can send you in very wrong directions. Is looking at the LTC 6813 datasheet, which is a commercially available chip, broadly the same as the Batman's, but also subtly different. But it can give you little hints of where to look for things and that, because there is some similarity in how they did it. I'm sure LT, you know, based this design for Elon on one of their existing ones. So there is some things in there, but it can also lead you down a rabbit hole that you then have to climb your way back out of. So, yes, please don't go reading that data sheet and then telling me what you know things are where and that, because most of the time they're actually not there. And ask me how I know that. All right, so I do have this code, so I do have this code on GitHub. I would ask people not to, you know, start downloading this and compiling it and trying to do stuff with it at the minute, because it is very much in flux. It's only beginning to take shape here, as I've shown you, but it is here and you'll see it. You know, it'll be getting updates and so on. This is the software repo, and there's a link down here to the hardware repo. This is the existing one from, look at that, 3 years ago. There it is. So this is where I've all the kind of SPI captures, a lot of reverse engineering, a lot of info and links and stuff going on here. And there was a lot of different ways I was going to go at this, but definitely the way to just get us something working here is going to be this particular way here, just using our trusty Batman chip. So, all right, I'm going to wrap things up here because probably gone on for long enough. So what I'm going to be doing is hopefully over the next week or so, I'm going to get a couple of these made up in the enclosures, and we'll get a few of these out to beta testers. So it'll be a couple of people that ideally, what I'd really like is someone that had a full pack. It doesn't really matter the capacities, you know, the boards don't really care about that. Ideally someone that had a full pack, maybe someone that had 1 or 2 modules, so just to get a little bit of feedback there. So ideally 2, maybe 3 boards going out there at the most, because it'd be just, it's very easy to overwhelm me with things. So that's what we'll be doing. Once you get a bit of feedback from that, there'll be bugs and cleanups. I can do a little bit of cleanup here with my mini Musk, but I'm sure there'll be things I've done wrong for full pack reads and all that sort of thing. So once we get that, then I would like to think that definitely within the next month we'll have these guys, these boards available in the web shop for you to purchase and enjoy. So what you'll be getting will be the board, the Wi-Fi module. There won't be a header or an enclosure, but they're just AliExpress, and you're like 10 or 12 euros, and you get the plug and the pins and the whole lot for that. Won't be supplying the Batman chips obviously on there. You'll have to get those yourselves. Now there's one, yes Watson, there's one advantage of having been away from this for the few years, is that there is bound to be a lot of those BMB boards that people have ripped off packs and have put other battery management systems on there. So I wouldn't think it'll be too hard, particularly if you get a little bit of community going on around the forum and so on, to get yourselves Watson cats to get yourself some Batman chips. Watson, really? You're going to pick now? You're going to pick now, right? Well, I'm okay. Cat logic. So anyway, yeah, it shouldn't be too hard to get Batman chips for your. Really, Watson? This is Watson. Okay, so it looked like something out of a James Bond film. It shouldn't be too hard to get yourselves some Batman chips. So for folks that are looking to use this board, might be kind of worth, now would be the time to you know, start looking around for some of those boards. So Watson and I will get back to work here, and we will see you next time. And as always, don't forget to give this one a thumbs down. You shouldn't have been watching it anyway. You should have been getting a funny cat video for yourselves. Great. That's great, Watson. Why don't we do this again? Okay. So anyway, we'll see you in the next semi-exciting episode. Don't share this thing with your friends, because you won't have any, you'll just have cats. And until next time then, happy Elon brain surgery, I guess. Watson, really? Timing, Watson.